This is the second part of Autumn 2 Week 1 exam practice marking video. So the question for 2C Part 2 is, in terms of bond energies, explain why this reaction is endothermic. And just to recap, without having to turn the page, the bond energy of the reactants was 1,443, for products was 1,260, meaning that there was a positive overall energy change of 183 kilojoules. Now, that's endothermic. I want to go over why. Okay, just to recap with you, on the reactant side, bonds are broken, which requires energy to be taken in. On the product side, bonds are formed, meaning that energy is given out. Now, if the reactant's bond energy, we'll just write in kilojoules per mole, is greater than the product's total bond energy in kilojoules per mole, that means that more energy is taken in than is given out. So if I write an example here, it could be like 5,000 kilojoules taken in, whereas there are only 4,000 kilojoules given out. So actually, taken in 5,000 kilojoules, given out 4,000 kilojoules. That would mean that we have a positive overall change of energy of 1,000 kilojoules. That means that 1,000 kilojoules are taken in, because the additional bond energy is on the reactant side, and that is the energy that is taken in. And we know that if more energy is taken in than is given out, which looks like this, so more energy, so we start with reactants with a lower energy, and we end with reactants with a products with a higher energy. We've got to draw our activation energy. It's an endothermic reaction. So this means that energy has been taken in from the surroundings. And just to recap over what we've gone through, in this example, more energy is taken in than is given out. And we know that when more energy is taken in than is given out, it's an endothermic reaction. So, energy taken in to break bonds, which is 1,443 kilojoules, is more than the energy released when forming new bonds, which is 1,260, and that's the answer. Next question. Methanol can be made by reacting methane and oxygen. The reactant is exothermic. So that means that less energy taken in than the energy given out to form new bonds. And we know given out energy, exothermic. The equation, the energy level diagram given below. Now let me remind you, we want to label this, not that we're going to get any marks for it necessarily, but it's just good to remember how to do so. So if we draw an arrow from the horizontal line from the reactant up to the highest point, that's our activation energy. And if we draw an arrow to the products, in this case which is down, that tells us the overall change in energy. Now here we've got the reactants, and they have more energy than the products. So energy here has been given out. So some of the energy that the products have, the reactants don't have. So some energy given out to the surroundings. How does the diagram show that the reaction is exothermic? Well, so I've just talked you through that. The energy of the reactant is greater than the energy of the products. That's it. A platinum catalyst can be used to increase the rate of this reaction. In terms of explain in terms of particles and the activation energy of a reaction, how a catalyst is able to increase the rate of reaction. So catalysts provide an alternative pathway with a lower activation energy. And if I was to draw this lower activation energy, it would be like this. So yes, there is still an increase in energy that every particle is expected to reach in order to react, but it's lower, which means that more particles have the energy to react, or required to react. Next, the equation can also be written showing the structural formula of the reactants and the product. So 2 reactants and 1 product. Use the bond energies given in the table to help you calculate the energy change for this reaction. Okay, so we'll start with the reactants as we did last time. So first of all, we have got 1, 2, 3, 4 bonds between hydrogen and carbon. So that's 435. Now, 4, 3, 5. But there are 2 so I'm going to do 435 multiplied by 4, which gives me 1,740. There's actually 2 molecules of this molecule, which is called methane. So I'm going to multiply that by 2 to find out the total bond energy of the methane reacting, which I need to write multiplied by 2, which gives us 3,480. So that's the total bond energy required to break the bonds between the 2 methane molecules. Then we've got just 1 oxygen bond. It's a double bond, so it's 497. So I'm going to write 340 plus 497 equals 3,977 kilojoules. I haven't left much space for the products. So we've got 1, 2, 3 hydrogen carbon bonds. So I will write that out now. 3 times 435 equals 1,305. Then we have 1 carbon oxygen single bond, which has a bond energy 336. So I'll add 336 to that, and 1 oxygen hydrogen bond 464. So the total bond energy of one of these molecules is, let me plug that in, 2,105. If you can see, there's a multiplier 2 in front of this molecule as there was in front of methane. So now I'm going to multiply this by 2, which gives me 4,210 kilojoules. Now remember, to find out the bond energy, I meant total change in energy, you take the products bond energy away from the reactant's bond energy. So we've got 977 take away 4,210, and the answer is negative 233. That's the energy change. Now, the next question. In terms of bond energies, why is this an exothermic reaction? Okay, so more energy is released to form new bonds of the products than taken in to break bonds of reactants. So more energy to form new bonds than to break old bonds of the reactants. And then they've given us an equation for the reaction of ethene and bromine. They told us the reaction is exothermic, complete the energy level diagram, label activation energy and energy change. Well, we're confident of that, and I've shown you examples of doing it. They've said that it is exothermic. Now, an exothermic reaction, you've given out energy, so the products have less energy than the reactants. So reactants have more energy than the products, and we always draw the activation energy in, linking them, and then you draw a line from, I'll just dash it, from the reactants horizontally, draw up to the highest part and label activation energy, and then draw from this line to the products, and that's your total energy change. There we are. Okay, next. The equation for the reaction can be represented as, use the bond dissociation energy, so that's these, to calculate the energy change. Okay, so again we'll do reactants, got 1, 2, 3, 4 carbon hydrogen bonds, 413 times by 4, which gives us 1,652. Then we've got 1 double carbon bonds plus 614 equals 2266. Then we've got a single bromine bond, which is, we'll add 193 to that to give us a total of 2,459 kilojoules. Now the products. We've got 1, 2, 3, 4 carbon hydrogen bonds. So again 413 times 4, so we know it's 1,652, plus we've got 1 carbon bond 348, which equals 2,000, and we won't forget these 2 carbon bromine bonds, so plus 2 times 2,276, which equals 2,552 kilojoules. Now, remember, total change in energy, the amount of energy taken in to break the bonds of the reactants, take away the total amount of energy released to form the bonds of the products. Substitute what we know in, and the answer is negative 93. And so we can check. So there was more energy in the reactants than the products, so energy was given out. That tells us that it's an exothermic reaction. Oh yes, and our other check, exothermic reactions always have a negative energy change. Okay, we're on to the penultimate page. So, the reaction is exothermic. Explain why in terms of bond broken and bonds formed. Well, reactants, energy is taken in, bonds form. With bonds broken, that's the reactants, and energy is taken in to break the bonds. When bonds are formed, what energy is released, and that happens on the product side. And with that reaction, let me just remind you, we calculated the change in energy by taking away the energy taken in to break bonds, taken away by the energy released to form bonds. So there's more energy released to form bonds, and the answer is that less energy is taken in which is 2,459 to break reactant bonds, than the energy released to form product bonds. Okay, next. The reaction of methane with steam is used in industry to make hydrogen. The second stage of this process is represented by this. Calculate the net energy transfer. I've done this one for you because we've done so many before. So the total energy taken in to break the reactant bonds, 2005 kilojoules. To make the product bonds, 2046. Change in energy, reactants take away products, and we end up with a negative change. What did we say that was? Exo or endo? You're right if you said exo, and therefore I've said it's exothermic here. With reference to your calculation, how do you know? Well, the idea that more energy is released, forming product bonds, than taken in to break reactant bonds. Now I hope what you got from this is to see actually there's a limited number of questions that generally are asked at GCSE with regards to endothermic and exothermic reactions and reaction profile diagrams and calculating the change in energy, and hopefully if you go through this and you really know your stuff, you'll be able to get full marks on any of those questions.